All right, guys, let's get into some trigonometry and some triangles and all that fun stuff. So, just a couple things, some previous assumed knowledge. Again, with all triangles, right, we do have the angle sum of 180 degrees, no matter what. Okay, so that's kind of something that's going to be something we can use. But then when we get to right triangles, okay, of course, triangles that have a right triangle or right angle, I should say. That's when you get the all the SOH CAH TOA stuff. We're actually going to review that in this video, where it can help you find side lengths or angle measures, okay, using the three trig functions, sine, cosine, or tangent. And you also, of course, have the Pythagorean theorem that holds with right triangles that talks about the side lengths, okay, the a squared plus b squared equals c squared, where C, of course, is the hypotenuse, okay? And that hypotenuse is something that comes up with the sine and cosine functions, and that's why you need to have a right triangle for those to work, because you have to actually have a hypotenuse. And this is kind of going on behind the scenes in all these trig functions. So let's take a look at a few examples. We'll definitely need a calculator to work some of this stuff out, and let's set up some problems. All right. So first off, there are two special right triangles that we need to be familiar with. One of them is the 30, 60, 90. Okay, so on that one, the way I want to kind of set up the side lengths is basically we're going to treat each side of an equilateral triangle to be 2x. Okay, and it's just going to make my demonstration of why some of these things work. Using 2x as the side length will make it work a lot nicer. So this is an equilateral. So of course right now we have 60 degrees on each, okay, because each triangle adds up to 180. So if they're all the same, it would be 360-degree angles. And what I want to do is actually draw an altitude straight down here, okay, and create this new triangle, a right triangle now. Let's just use this one, let's say, boom, 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 okay. And I'm going to just bring this out here so we can kind of use it as our example, okay? And let's think about what we have going on. So that, of course, is the right angle. This is the 60-degree angle that was right down here. Okay, this is right. So that leaves, if the angle sum is 180, we have a 90 and a 60, so we have a 30-degree angle up here, okay? And from the figure, this side right here is the 2x side, okay? So what ends up happening is that the side length down here, the bottom, if the whole length is 2x, okay, that means this side is x and then that length would be x. So for our picture, our diagram, we are going to have x as a side length down there. Okay, so what I want to do is take a look at what would this other third side length over here end up equaling. And to do that, we can use Pythagorean's theorem. Okay, so what it says, let's just call this a, just so we can give it a name. So basically we have a squared plus x squared. The hypotenuse is 2x squared, okay, Pythagorean theorem. So a squared plus x squared equals, if we take 2x and square the whole thing, we're actually going to get 4x squared. Then subtracting, because I'm trying to solve for a, so if we subtract x squared from both sides, 4x squared take away an x squared is going to be 3x squared. And then what we can do is a squared here. To solve for a, we will take the square root of both sides. Okay, square root here, square root here. So a is going to equal the square root of 3x squared, okay, which is the square root of 3 times the square root of x squared. And the reason I want to write it that way is because we know the square root of x squared is just x. So it's going to be x times the square root of 3. Okay, so that's going to be this side length here, x times the square root of 3. Okay, and remember, x is just whatever that little side down there is. Okay, so now we know, no matter what the short side is, okay, x is the shortest side of the triangle. We know that the hypotenuse over here will be twice as long. And the middle length here, the second longest side, will be square root of 3. So let me just rewrite this one more time a little nicer. Let's say here's our 60, here's our 30, here's our 90. So again, if you notice, we have the smallest angle gives us the smallest side across from it. Okay, the medium angle, 60, gives us the medium side across from it. Square root of 3 is about 1.7. And then the biggest angle, of course, the 90-degree angle, gives us the hypotenuse, which is the longest side, which is about 2 times x. Okay, so if you know any of the sides, and then you know it's a special triangle, 30, 60, 90, you are able to find the other two sides. You only need to know one of the side lengths to do that. Okay, and we'll look at an example in a minute here. Okay, so let's dig in a little bit more with the trig functions. Okay, so again, here's our picture. Here's our 60-degree angle. And the triangle can be rotated, you know, any way you want, as long as you get the correct side opposite the correct angle. And the way this works is the shortest side is what we're calling x. Again, the hypotenuse is 2x, and then we just found over here the x root 3. Okay, so let's take a look at sine, cosine, and tangent of the 30-degree angle, and then also of the 60. Okay, so as a quick reminder, okay, sine of any angle will always be the opposite over the hypotenuse. Okay, the cosine of an angle will always be the ratio of the adjacent side over the hypotenuse. And the tangent of any angle theta will be the opposite over the adjacent. Okay, so we're assuming we have some knowledge of that. Remember the SOH CAH TOA stuff. So for this specific triangle, if we focus in up top here on the 30-degree angle first, so right here, okay, the sine is going to be the opposite side. So opposite side is all the way through the triangle over the hypotenuse, which is 2x. Okay, and if we reduce that, 1x over 2x, okay, if the x's cancel out, the sine of 30 degrees is 1/2. Okay, for, oops, let me erase that. Cosine for 30 degrees, let's get this out of here. Cosine will be the adjacent side over the hypotenuse. So from our 30-degree angle, the adjacent side is the side right next to the angle, which is not the hypotenuse, so the x root 3 side over the hypotenuse of 2x. And simplifying that again, the x over x cancels out, so we just end up with the square root of 3 over 2. Okay, now for the tangent of 30, okay, again, if 30 is our reference angle here, the opposite is down here, the adjacent side is over here, so the tangent would be x over x root 3. Okay, what ends up happening, the x's do cancel, so we're left with just a 1 over root 3. And we're going to find we cannot leave a irrational number, or I should say we cannot leave an irrational number in the denominator, so the trick around that is to multiply top and bottom. This is called rationalizing it. We multiply top and bottom by root 3, and we end up with root 3 on top, and then the denominator, root 3 times root 3 is root 9, which is just regular old 3. Okay, so the tangent of 30 will be the square root of 3 over 3. Now these values, okay, are going to be very, very important for us. Okay, knowing the sine of 30, cosine of 30, tangent of 30. Okay, you may remember they come up in the unit circle a lot. So the unit circle is another way to kind of come up with these values. There's a whole bunch of patterns, but knowing these special right triangles is another really big way. Okay, so you're going to have plenty of options in this unit. You just need to decide or come up with one that works best for you so that you can have these values in this process together. Okay. All right, let's move on to the 60-degree angle. Okay, so if we're talking about the 60-degree angle now, the opposite side is now over here. The adjacent side is down here. Okay, and then the hypotenuse is always locked in over there. Okay, so for the sine of 60, we're going to do the opposite side, the x root 3 over the hypotenuse of 2x. Okay, and again, the x over x cancels out, so the sine of 60 will be the square root of 3 over 2. The cosine of 60, we're doing the adjacent side over the hypotenuse, so x over 2x. And 1x over 2x reduces down to 1/2. And then for tangent of 60, opposite over adjacent, so x root 3 is the opposite, x is the adjacent, the x's cancel, the tangent of 60 is root 3. Okay, so again, with these, you can of course type those into a calculator or whatever, and it's going to give you a decimal. So with the 1/2, that's fine. But like for the ones that are root 3 or root 3 over 2, I'm expecting you to know these values exactly. Okay, I don't want 0.707 or whatever the root 3 over 2 is. I want it to be written as root 3 over 2. All right, and let's take a look now with the 45, 45, 90 is our other special right triangle. Okay, this is the other one where we need to know the values of. So I just kind of drew an example here. So let's say it's 45, 45, and 90. So the deal with this one, okay, where things come from on this one is that when you have the two 45-degree angles, that means the two legs across from them are going to equal each other. Okay, so let's just call them both x, right? They could be anything, but they're both going to be the same. So the hypotenuse over here, how does it relate? Okay, let's again use Pythagorean's theorem, which says x squared plus x squared must equal c squared, right? A squared plus b squared equals c squared. Simplifying, x squared plus x squared is 2x squared equals c squared. And remember, we're solving for c, so we take the square root of both sides. C is going to equal the square root of 2x squared, okay, which just like before, we can simplify. We can separate it. The square root of x squared times the square root of 2. Okay, and the square root of x squared, of course, is just x. So it's going to be x times the square root of 2. Okay, that's going to be the length of the hypotenuse. Okay, and just for the sake of visualizing that, square root of 2 is about 1.4-ish. Okay, so in a 45, 45, 90 triangle like this, the hypotenuse is about 1.4 times longer than either leg. Okay, all right, so let's think about the sine, the cosine, and the tangent. Okay, now for the 45-degree angle, since there's two of them, right, it doesn't matter which one we use as our reference. Let's just say that's it. So this over here would be the opposite. This down here would be the adjacent. And notice they're both the same, okay, for this special triangle. And of course the hypotenuse over there. So the sine of 45 is opposite over hypotenuse, okay, x over x root 2. Okay, if we think of that as 1x, it'll end up canceling the x's, 1 over root 2. And just like before, we're going to get that denominator to become rational, multiply top and bottom by root 2. So we are left with the square root of 2 over 2. Okay, that's going to be the sine of 45. Okay, I think that's the one that's the 0.707. I might have said on the last page. Cosine of 45 is the exact same thing. Okay, opposite and adjacent are equal. So the cosine, the adjacent is x, hypotenuse is x root 2. It's going to simplify to the exact same thing. So the 45 is really kind of a nice angle because the sine and cosine are equal. Okay, and the other really nice thing about this, as far as having to memorize a bunch of stuff, the tangent for 45, opposite over adjacent, x over x, tangent of 45 is just 1. Okay, so that's kind of nice. We don't have to worry about, root 3s and all that stuff. So the 45s, like I said, I think are the nicer of the two. And then it's with the 30s and the 60s, we kind of just need to get some sort of pattern. And that'll come as we practice and do more and more with these. We kind of already worked it out over here. Remember, when the legs are x, the hypotenuse is just going to be whatever x is times root 2. All right, so let's take a look. Let's see if we can find all unknown side lengths on these two. And a hint, these are special right triangles, so we really can do these without knowing any of the sine, cosine, tangent stuff or calculators. We probably could have done this slide before we did the sine, cosine, tangent stuff, but here it is anyway, so let's do it. All right, so first off, the triangle on the left, okay, we have a 45, 45, 90. One of the legs is 6. Okay, so again, kind of start getting in the mindset of thinking, all right, if that's 45 degrees and that's 45, I know the sides across from them need to be equal to each other. So that side would need to be 6 as well. These are kind of like the x and the x. And now, what was the rule for the hypotenuse? Okay, you can use Pythagorean theorem, you can use whatever you want. So on this problem, if the legs are both 6, the hypotenuse is going to be 6 times the square root of 2. And we can leave it just exact like that. We don't even need to multiply that out. It's kind of cool. All right, we did that. No calculator, no nothing. All right, so example 2, 30, 60, 90. Okay, we have the hypotenuse is 8. We don't know either of the other two. Okay, so again, Pythagorean theorem is not going to work. It's not going to help. We only know one side. So what we need to remember on this one is the short side is we call x. The hypotenuse is twice as long. And the medium side, across from the middle-sized angle, is x root 3. Okay, so what we can do there, now that we know the 2x side equals 8, okay, we know that the 1x side over here must be half of that, or 4. And then this medium size of x is 4 will just be 4 square roots of 3. Okay, now the good news again with these, if you're not feeling it or whatever, you can always do some of the other stuff we're about to do with a calculator and use the SOH CAH TOA stuff and find these. But it's just a little quicker, and you can know these exactly without a calculator, just by knowing those special ratios and stuff like that. Okay. All right, so let's take a look. Here's some other type of problems, quick review that we're going to need to know how to handle. All right, so we got this little triangle here. It is not a special right triangle. There's a 27-degree angle in there, okay? That's going to be your hint. Our calculator's got to come out. Okay, so let's think about this. We have the 27-degree angle here. We can use that as our reference. So what that means, if you just want to get things labeled, the opposite side is down there. Of course, the hypotenuse over here across from the right angle, and that leaves x to be the adjacent side. Okay, so what I'm thinking in this problem, we don't have the opposite side. We don't really need it. Let's just deal with adjacent and hypotenuse. Okay, so that is cosine. So I know the equation is that the cosine of the angle in degrees equals the opposite, cosine is adjacent over hypotenuse. Okay, so x over 16, and we want to solve this for x, right? So what we're going to do is multiply both sides by 16. 16 times the cosine of 27 degrees equals x. Okay, now one thing before you throw this in a calculator, make sure at this point we are in degree mode. Okay, if you don't know where that is on your calculator, look it up. It's very, very important. Okay, and you can see if you get the same answer I get. But 16 times the cosine of 27 in degree mode is giving me a value of 14.26 for x. Okay, some calculators might require you to do the cosine of 27 first. You might have to press 27 and then the cosine button. It'll give you some decimal and then times it by 16 after. But the graphing calculators and stuff will let you type it in just like that in one strand. Okay, and always make sure your answer seems reasonable. Okay, the hypotenuse was 16, so does 14.26 seem about right? You know, it seems like it's in the ballpark. All right, let's set up another one here. So we have this right triangle kind of flipped around a little bit. There's a 70-degree angle. So that means the side opposite it over here, that's the opposite side. Maybe we shouldn't write with the highlighter anymore. The hypotenuse is down here because it's across from the right angle, and then the x is the adjacent side. So our problem again here now, 70-degree angle, we have the opposite and the adjacent. Hypotenuse is not in the mix here, okay? So that's going to eliminate using sine or cosine. We're going to have to use tangent here. Okay, so we know that the tangent of the angle, 70 degrees, equals the opposite side length over the adjacent side length. Okay, we're going to solve for x. Since it's in the denominator, let's multiply both sides by x. X times the tangent of 70 will equal 14. And then we're going to get x by itself by dividing both sides by the tangent of 70 degrees. Okay, so again, another calculator problem. Make sure you're in the correct mode. 14 divided by the tangent of 70 is giving me 5.095. Let's call that 5.10. Okay, and that would be our side length we needed. All right, how about using this stuff to find angle measures, right? So in this case, we know two of the side lengths. What we need is that angle down there. Let's think about from that point of reference, which sides are we dealing with. So I know, again, it might be best to label the hypotenuse right away. That's kind of locked in based on where the right angle is. So then down here, this is the adjacent side because, again, the side all the way across would be the opposite. So the 21 ends up being in the adjacent spot. And in this problem, we're not using opposite at all. Okay, so I can't use sine, I can't use tangent, I have to use cosine. Okay, so the cosine, we usually use theta for an angle measure. You know, you can use whatever variable you want. But the cosine of some unknown angle theta equals the adjacent side over the hypotenuse. Okay, and this problem's a little different, right? We know both side lengths, we don't know the angle measure. So what we need to do is solve for theta, okay? And the way we're going to do that is we are going to do what's called an inverse function, right? We need to get rid of this cosine here, okay? And it's not just like dividing. Our problem is not cosine times theta, it's cosine of theta. So the way to get rid of that is to do the inverse trig function to both sides, okay? Your calculator has a button that knows how to do this. Okay, we're going to take the inverse cosine of both sides. What it's going to do is cancel out or undo having that cosine there. And we'll just be left with the theta is the cosine inverse or inverse cosine. In your calculator, you're just going to type it in as a fraction, 21 divided by 55. So it's usually pressing the second button, second cosine, you'll see the little -1. 21 divided by 55, still in degree mode here, gives me an answer of 67.6 degrees if we round that up. And that is how you find angle measures. Okay, so again, this is a basic intro review, hopefully for pre-calc level, of using SOH CAH TOA with right triangles to find angles and sides.